Hello everyone, welcome back to another video in the LLMs related playlist. In this video, we are going to see how to apply direct preference optimization method on top of the latest state-of-the-art model, which is Mistral. This approach has been used by the Hugging Face team to create a chat beast, if you want to term it that way, known as Zephyr. This model has outperformed ChatGPT in the Alpaca eval benchmark, and also it has outperformed Llama 270 billion chat almost in every benchmark. Okay, so the approach which they have used is known as distilled direct preference optimization. So distilled direct preference optimization is named as such because it uses a direct preference optimization method on top of a knowledge distillation being performed. So here the knowledge distillation is performed by taking the responses from other models and ranking it with the help of GPT-4. So before going on to the coding part, let me just give a gist of direct preference optimization. And if you want to know in detail about direct preference optimization, there is a video in our channel, so I would recommend you all to check it out. The link is in the description. Direct preference optimization is a method which has come as an alternative to RLHF to help the models to align its response to human preferences. Okay, so followed by that, there were a lot of papers coming up in this specific domain. The main problem in RLHF was that it needed lot of computation because you need to train a reward model and then use that reward model to reward your own normal model. Okay, so it was a lot of time consuming and resource consuming process which was optimized by DPO. But still in DPO there was a problem, not in performance wise. What happened was still you needed a preference dataset where you need to have two responses for a given input. One is chosen response and then one is rejected response. Human annotation for that specific dataset is too hard, so you need to have one response which is correct and one response which is wrong. It will take a lot of time. So then a paper known as RLAIF came from Google DeepMind themselves. So what they did was they took responses from GPT-4. So they had GPT-4 to rank the responses, but to generate these responses there came a paper known as UltraFeedback. Okay, so there was this OpenBNB organization who released UltraFeedback dataset. What they did was basically, given a prompt, they'll try to find responses from 4 different models and then they'll rank it with the help of GPT-4. Okay, so basically there is a knowledge distillation being performed there. So that is how Zephyr used DDPO to create such a big model, and we are gonna do the same thing which they did but in a smaller scale because this is a teaching video, right? Not an industry scale thing, because we don't have such an environment to do it here. So the first step would be, if you want to replicate this Zephyr 7B, what I would recommend you all to do is do a normal fine-tuning of Mistral on top of this specific model known as Mistral 7B SFT Alpha. You can follow the same code which I have explained in the previous video of fine-tuning Mistral, where fine-tune first on this model, Mistral S7B SFT Beta, which is your SFT model, because before doing DPO you need an SFT model and then you will do DPO on that model. So first I would recommend you all to do this. For now, what I did was I took this model from the blog /OpenHermes Mistral 7B. So this is also a kind of instruction tuned model. Okay, so this has been a pretty good model. So what I did was I took this model, not GGUF but GPTQ. Okay, I've taken this model as our SFT model, and on top of that I've replicated the same pipeline of Zephyr of using UltraFeedback with the DPO mechanism. So let me show you the UltraFeedback dataset now. UltraFeedback, and I'll explain the dataset also. So here you can see this is the UltraFeedback dataset, and this is how the dataset format is. So this dataset is MIT licensed, so anyone can use it for your use case, and it has around 62,000 dataset points, which is pretty good a size for a mechanism like DPO, which is used to align the responses. Okay, so for any given instruction, 4 models are provided. Okay, for 4 models this instruction is provided as input, and 4 models will provide a completion, and then what they'll do is they'll try to evaluate it under different categories: instruction following, honesty, truthfulness, helpfulness, and based on this they'll try to provide an overall rating as well. Okay, so based on this, the top performing model, let's say here it is GPT-4. So here what they will do is GPT-4 will be the preferred response, and one of the other 3 will be the dispreferred response. So this is how they created this specific dataset known as UltraFeedback binarized. So UltraFeedback is the source data, but they did do something called processing, which they vaguely termed with these things which I said, like you can just do some processing, and then based on the rating we chose it. So that is how they would have specified it, and we'll also do the same thing. Okay, so I'm searching for Zephyr collection. Here it is. We are not going to do that processing also, but it will require some processing from us. We are going to use this dataset known as UltraFeedback binarized. What they did was they did all the prior things which we said, be it like choosing the best response and then one of the other 3 as the rejected one. So here you have, right, chosen, rejected. For DPO, the input must be a triplet: a prompt, a chosen response, and a rejected response. Okay, and that is how the dataset it is there here. But here also it requires some processing, because here you can see, right, it is a dictionary, and inside the dictionary there is a role of user and content from the model. Okay, because here if you see, this dataset can be also used for optimizing models like Flantify, because it is not just a DPO method is a method which can be used only for decoder only models. No, you can use it for any model, be it encoder, decoder, or decoder only. So they have provided it here, but we only need the assistant one because prompt is provided here. Okay, so what we'll do here is, this is the dataset. So first we'll install the dependencies, which is Torch 2.0.1, transformers, datasets, PEFT, accelerate, TRL, bits and bytes, optimum, and auto GPTQ. Torch is there is a version issue, so I recommend you all to install this version 2.0.1. And then transformers, it is the core library. Datasets to interact with the Hugging Face dataset hub. PEFT is for having the LoRa adapter, and accelerate is for having efficient GPU and CPU computing, and TRL is kind of another core in our process here, because that is the library which will provide us the trainer known as DPO trainer. So TRL stands for transformer reinforcement learning. And we have bits and bytes, optimum, and auto GPTQ. Optimum is a sub requirement, and auto GPTQ is a requirement to work with GPTQ quantized model. Okay, so once you have installed the dependencies, the next step is to import the dependencies, which is import Torch, and then from datasets we'll import the dataset class and load dataset to load a specific dataset by their dataset ID, and dataset class to have some functions being performed on top of the dataset class. Okay, we have auto PEF model for COS LLM, LoRa config, get PEF model, and prepare model for KPIT training being imported from PEFT. Auto PEF model for COS LLM, it is used to wrap a model with an adapter based on the config provided, and then LoRa config is used to provide the configurations for LoRa adapter, and get PEF model will take this config and the base model, and it will try to attach the adapters to the base model. And once you have done that, the model should be prepared for quantized training, for which we'll use prepare model for k-bit training, which is 4-bit training here. And then we have auto tokenizer, training arguments, auto model for COS LLM, and GPTQ config being imported from transformers, and also DPO training. Now the first step would be to log into the notebook. So click the login, provide your access token, and you are done. Next is to create the data, for which the first step is to load the datasets, and here I'm considering the split as test prefs. So if you are doing it for large scale, I would recommend you all to do it on train prefs completely. Okay, and even I didn't run it for complete dataset. I just ran it for around 100 or 200 data points actually. Okay, so you have the dataset dot column names as the original columns, because we'll remove all these columns from the dataset. Now next we have return prompts and responses. This is a sub function which is used so that we can provide the dataset as required by the DPO trainer, because it will take three inputs, which is prompt, chosen and rejected. For prompt, we'll go through the samples prompt and then we'll provide the prompt there, and chosen will take the chosen and then rejected as rejected. Okay, so as simple as that, we'll make the dataset more formatted as per the user input. But the problem is there still. Okay, I'll show about that in the later part. So the first step after this is to load the tokenizer. So here you can see we are loading the OpenHermes 2 Mistral 7B GPTQ tokenizer, and we are setting the padding token to be EOS token. Okay, and now what we are doing is, this is a very important step, guys. We'll have two instances, one is model and another one is model ref. Okay, both will load it in the same way, because in case of DPO, your model will act as the reference model as well, which will try to optimize the loss. Okay, so to know about the in-depth working, like I said, see the DPO explanation video. You will get an understanding of how this happens. Okay, so now we are loading the model OpenHermes 2 Mistral 7B GPTQ with the D type being torch.float 16. We are setting that the memory usage should be less by setting low CPU memory usage to be true, and quantization config, for which we provided GPTQ config with the bits being 4 and disable exclama is set to true, so that we are saying that we are doing some training on GPUs. Okay, now we are creating the dataset, and in dataset, if you see, there is content here, right? So now, like I said, we need only assistant's response, not the user content. So we need to do an apply function. So what happens is, once you go into this, it will have two dictionaries. Okay, in chosen there will be two dictionaries. One is from the content and response of user, and then the same one for assistant will take the second dictionary, which is the assistant, and inside that we'll go for the content. Okay, so now we'll take the same one for rejected as well. Then we'll drop the missing values if there is any, but it wasn't there, and we'll also take some random 10 samples, because with DPO it's very important to have a validation set. Okay, so now since the processing is completed, we'll convert this pandas data frame into Hugging Face dataset by using the dataset class by calling the from pandas function, which will take the pandas data frame. Now you can see, right, the train data has three features, or three columns rather. Here it is prompt, chosen and rejected. Now coming on to the model, if you print the model, it will be normal. There is 32 layers with the class name being Mistral decoder layer, which has two specific main classes. One is a rotary embedding, and then Mistral MLP, and in inside the Mistral attention, and then Mistral MLP. Inside that Mistral attention, they have rotary embedding, KProj, VProj, OProj, QProj, VProj. Everything is there, and similarly Mistral MLP also contains different things inside that with some layer norms there. But while optimizing the model, we'll focus on K projection and V projection as specified. Sorry, Q projection and V projection as specified in the LoRa research paper. So for providing LoRa config, we have provided the rank as 8, alpha again being 8, LoRa dropout being 0.1. The target modules is Q projection and V projection, QProj and VProj. And then we have the bias is set to none, and task type is causal LM, because this model is a causal language model. We are also setting the PEFT config inference mode as set to be false. You can also provide this here, but I thought, okay, let's provide it here, because if you don't provide this, you will run into some errors. Okay, next, what is the step is to prepare the model for fine tuning, because we have the base model, which is the reference model also, so that is ready, but we are not prepared for fine tuning because we need to attach the model with the LoRa adapters, and also we need to prepare the model for the quantized training, right? So first what we are doing is we are preparing the model for quantized training. We are setting the use catch to be false, so that it will know, okay, we are training, not inferencing, and we are setting the gradient checkpointing enable is set, and then we are calling the pre-training TP is equal to 1 is set, so that will replicate the pre-training training performance will be not disturbed, and it will try to increase the performance from there. And then get PEF model, which will take the model and PEF config so that we can attach the adapters to the model. Okay, so that is the base model, and similarly the process is replicated in reference model as well. Next we have the training arguments, where I have provided the batch size as 1, max step is 50, and then we are saying remove unused columns equal to false. Keep it there, because at sometimes you might run into errors without that. And then gradient accumulation steps is 1, learning rate is 2e minus 4, but in Zephyr paper it would have specified as 2e minus 5, so if you want you can try that as well. Evaluation strategies steps, logging first step is set to true. Okay, so first step will be logged, and then for every 10 steps the logging will perform. And the output directory in which I need to store all the model and run configurations, everything is OpenHermes Mistral DPO GPTQ. Optimizer which I'm using here is paged AdamW 32-bit, and warm-up steps is 2. I've said that we should train in float precision 16, which is mixed precision training, and then we are also pushing the adapters to the hub. Okay, so that is about the training arguments. So next we'll have the DPO trainer. So here we are calling the DPO trainer, which will take a lot of inputs. First is model, and then the reference model, both are same here, and then we'll provide the training arguments, which is from here, and then we'll provide a value called beta, which is to have some scaling in the training, which is 0.1 here. And then we have train dataset and val dataset being provided, followed by the tokenizer is also provided. The max length is set to 512, and the max target length is set to 256. This is something which is very much important to note. The total length of input is 512, but the prompt is 256 and target is 256. Let's say you have use cases like information extraction or something like that, in which you will have prompt length to be very huge and the target length will be very less. Okay, so in that case what you need to do is you'll need to provide the total length first. Let's say it is 1024 here, and then the prompt length is maybe 1000, and you can provide that here, and then the target length is 24, which you can provide in the max target length. Okay, so that is about DPO trainer. And then you can call the train function, it will try to train it, and here you can see there was a pretty good training actually. For just running it for 50 steps, it gave a good loss, and then the rewards were being optimized, and the performance was actually pretty good, so that you will see in some time. So now that the training is completed, you can call the push to hub function, so that you can push the model which you have into the hub, so that we can call it for the later part, which is inference here. Okay, so let me show that here. OpenHermes DPO, let me search if that is coming. Yeah, here you can see Vasant OpenHermes Mistral DPO GPTQ. So here is the model, and we'll use this model actually. Okay, so now that we have the model ready, we'll start with the inferencing part. Okay, for inferencing we have AutoPEF model for causal LLM being imported from PEF, generation config, so that we can provide the configuration for model generation, and then we have the tokenizer and torch. First we'll call the tokenizer from my directory itself, which is Vasant / OpenHermes Mistral DPO GPTQ. So here is it. Here it is. Okay, and the tokenizer was used to tokenize the input. So here we have provided an input stating that I have dropped my phone in water. Now it is not working. So what should I do now? Okay, so this is a standard question which I have used for a lot of models in previous videos, like XPNLM and DeciLM. There were a lot of models which I tested, and those were kind of good responses, but this response which I achieved now is probably the best response yet. So yeah, wait till you know that. Okay, so tokenizer, we are sending this input, and we are set that the tensors you should return is PyTorch tensor, and we are also setting the device to be CUDA. Okay, so now calling the model for which we have used AutoPEF model for causal LLM. So what it will do is it will try to do auto model for causal LLM, and it will try to load the base model, which is OpenHermes 2 Mistral 7B GPTQ. That will be loaded first, and then it will be attached with the adapters. Both will happen in a single step by calling AutoPef model for COS LLM, because the pef config file will have the base model as well. So let me show you here, adapter config.json, and here you can see the base model name is the blog/OpenHermes 2 Mistral 7B GPTQ. Okay, and it will have the other values as well. Okay, and here you can see there are some other configs. If you want, you can play with that. Okay, now we are setting the low CPU memory usage to be true, and then the return dict is also set to true. Okay, next we have the d type being set to float 16 and device map set to be CUDA, so that we'll be inferencing it in GPU. Okay, so that is how the model is loaded. And next we have the generation config, in which we have said do sample is equal to true, because when you give temperature, it is good to have do sample being set to true. And then we are saying that I need only the top response, for which we have set top k is equal to 1, and I've said that I'm allowing the model to generate 256 new tokens, which is set by setting max new tokens is equal to 256. And then here the path token ID is set to tokenizers EOS token ID. So with that, we have the model, we have the inputs, we have the generation configuration. Now try to the next step is to for us to try to integrate all of those into a single function, which is model.generate function, where we'll provide the inputs and the generation config. And once you get the outputs token IDs, we'll call the decode function of tokenizer, where we'll skip the special tokens and other tokens will be decoded and the string is printed here. So the question was, I have dropped my phone in water, now it is not working, what should I do now? Here it is said, if you have dropped your phone in water, the first thing you should do is turn off immediately. If it is still turn on, turn off. Then remove the battery if possible. If it is not removable, then leave the phone off for at least 72 hours. After that, try to turn on. If it does not turn on, you should take it to professional for repair. What should I do if my phone is not charging? So if your phone is not charging, so then what should you do? If your phone is not charging, first obviously you need to check the charger. If it is not working, then again there is a problem in your charging port, so you can try to clean it, and still if the problem persists, take it to the repair. And yeah, so let's say your phone is probably not receiving calls after that, which means like probably if the hardware is problematic. So what they are saying is like just check if your phone is in airplane mode or the signal is weak, and if it is not, then the problem is not there, then you should take it to a professional. So here you can see it was giving a pretty good response. So what I asked and what it responded was probably not a spot on result, but yeah, it does the work, right? When you put the phone in water, these are the things which we will do, right? So, and it gave that response. So that shows that this model has the capability to respond what we want it to respond. So that is the capability of DPO in aligning a model's response to user's preference. So that's it for this video, guys. I hope you all like this video. If you like the video, hit the like button, and it will help YouTube recommendations coming up to the channel, and share it with your friends so that they will also know how to align their models to their preferences. Also share your opinions in the comment section. I'll see you all in the next video. Until then, cheers.